Bismillah ar-Rahman ar-Rahim. So today, inshallah, we'll talk about. Today is the first time we'll get upstairs from the basement. So we'll go upstairs a little bit. So no more dealing with like ones and zeros in a form of bits or bit stream. So we'll go a little bit higher level and start dealing with frames. Before we start talking about packets in the next part of the course. So as we have discussed so far, the physical layer has two distinct functions, which are the encoding and signaling. And we talked about these two functionalities in details in the first part of the course. So in the second part, we'll start talking about data link layer. And as we have studied in 455, the data link layer is actually so we have the network layer, and we have, of course, the physical layer. And here we have the data link layer. The data link layer itself is actually subdivided into two sublayers. Okay, what we call the data link control, which is this part. Okay, and we have the medium access control. So we studied medium access control in 455. Okay, so we studied like Sysma CD and maybe Sysma CA and so on and so forth. Collision-based schemes and non-collision-based schemes and so on. So in this chapter, we'll talk about data link control. The data link control is the upper sublayer of the data link layer. The main functionality of the data link control sublayer are three things. Okay, so first, it's the first sublayer that receives packets from the network layer, and it needs to convert that into frames. So the first step is what we call framing. So the main functionality, one of the main functionalities of data link layer is actually framing. Two, the data link control performs what we call flow control. And error control. Okay, so it's framing, flow control, error control. So these are the three main jobs of the data link control sublayer. Of course, the medium access control sublayer, what it does is that it controls the access to the medium, whether this medium is wired, wireless, or whatever. Okay, so the data link control sublayer does not deal with the medium. So regardless of the physical medium itself, whether it's wireless or wired, the data link control sublayer is medium independent. Unlike medium access control, which is medium dependent. So the medium access control really depends a lot on the physical medium. And that's why we have Sysma CD for Ethernet. So for Ethernet, for wired networks, we have Sysma CD. But when we switch to wireless, we cannot perform any carrier detection, collision detection. We cannot perform collision detection, in which case we have to use Sysma CA or carrier sense multiple access with collision avoidance. So because we cannot perform any collision detection in the case of wireless. So therefore, the MAC sublayer is actually medium dependent, where the medium access control sublayer is medium independent. So it does not know anything about the physical medium. So all the three functionalities we have listed here, the framing, flow control, and air control, these are done regardless of whatever physical medium you have. So the first thing is that the medium access control will have to do framing. And framing is divided into two things. What does it mean to do framing? Framing is that when we send anything to the physical layer, it will go as a stream of bits, right? So who will tell the receiver that pay attention to the fact that from this bit until this bit, this is actually one frame? Okay? So from this point to this point, this is actually one unit of data that you have to start processing. Because as we all know, in the TCP/IP stack, each layer will have to encode and decode a header. Or in some cases, for the case of data link layer, we have header and trailer, right? So who will tell the receiver that from this bit to this bit, this is actually one unit that you have to start processing. And processing means you have to extract the header or the header and trailer and then start processing the header. And based on that, send the remaining data up in the stack and so on. So who will tell the receiver that this is the beginning of a frame and this is the end of a frame? So this is similar to the fact that when you send, if you want to send any information, even through postal system or something, this is similar to the fact that you have to put your letter in an envelope, right? And put the address on it and send it. Because if you don't do that, then your paper will go in the trash with millions of other papers that does not actually distinguish where this paper is coming from and where it's heading to or where it's sent to, in which case the receiver will never actually receive anything. So I have to have some boundaries, okay, to the inside the bits that will tell me, okay, this is the beginning of a unit and this is the end of the unit. And the unit for us in the data link layer is what we call frame, okay. So as we have discussed before, I can use what we all know as delimiter. Okay, so a delimiter is a special pattern, okay, inside the bit string that would tell me, okay, this is the start of the unit and this is the end of the unit. So when you go through the bits, once you see this pattern, okay, then you know all of a sudden that this is the beginning of the data unit or the frame. Okay? When you see it again, this is when you say this is the end of a frame. Okay? So actually before that, what we could do is that, just to make it simple, is to say that the frame length is fixed. If it's fixed, then I don't need any delimiter because all I need to do is just to count the number of bits. So if we assume that the frame size is fixed to, let's say, 1,000 bits. Okay? So every 1,000 bits, I'm going to stop and say, this is one frame. And then 1,001 will be another frame, and so on. So that's simple, and this is what we call fixed size framing. So fixed size framing is actually trivial, is easy. You don't need a special technique for that because you just need a counter. So the receiver will count until I reach 1,000, then I stop. As simple as that. Okay, so we don't need to talk about it because it's very simple. But the variable size framing is what we need to pay attention to because the frame size is actually variable. So in which case I have to use this delimiter to say this is the beginning of a frame and this is the end of a frame. So the variable size framing itself can be done using what we call special pattern or special delimiter. And for that, we can use a specific bit pattern to designate that this is the beginning of a frame or this is the end of a frame. So we use that, that flag as a delimiter to say this is the beginning of the frame. And then this means that whatever comes after this is actually the header, and we know the length of the header. So the length of the header is based on the protocol you use. So in that case, you know the length of the header. So you stop after the length of the header, and this is the beginning of your data. So you extract all your data, and then once you see the trailer, this means that the data has finished, and then after that, we should see the flag, or the end of the frame. This is when we mark that this is the end of the frame. And then the beginning of the next frame should be marked with a flag. This means actually that in between the frames, you don't need to trigger any decoding until you see the flag, which means that the sender can actually remain silent for some time. So I should not expect to receive, I mean the receiver itself should not expect to receive bits all the time. Because once I receive the flag, this means that this is the end of the frame. And I will not start taking any or processing any data until I receive this flag. In between, I could be just idle, not doing anything until I receive the flag. So this flag triggers the data link control to start receiving the bits from the physical layer, and then start processing it, which means extract header, extract trailer, and then process that based on the protocol. So there's one issue here. What is that? What do you think is the issue here? If I have a flag to mark the beginning and the end, I can make this flag like one character, let's say, like for example, 0, 1, 1, 1, 1, 1, 1, and then 0. So this is a flag. So I'm going to use this flag. This is a special pattern. So if I see 0 and then 6 ones and then 0, this means that, okay, this is the beginning of a new frame. So what is the issue here?
You shouldn't use this combination
in the data. برافو عليك. بالضبط كده. So what if this pattern exists here in the data itself? Okay? Because this data is coming from the application, and I cannot restrict this data to have no pattern like this. I cannot do that, right? So I have to have a solution for this. So this is the only issue with the framing. This is what we call, the first type of the variable size framing is what we call byte stuffing. And what byte stuffing means is that I need to use the flag or the 0 and then 6 ones and then 0. This is actually what's used in reality. And what I need to do is to perform what we call byte stuffing, which means that I have to go through the data itself. Whenever I see a pattern that looks like the flag, okay, I will insert escape character before it. This means that this is a trigger for the receiver, that whenever it sees the escape character followed by the flag, then it knows that this is not the end of the frame. This is part of the actual data, in which case it will remove the escape character and use this as part of the data. If I don't have the escape character followed by the flag, if I have the flag directly, this means that this is the end of the frame. So this way, I can simply end the frame here, if I don't have the escape character. Or I can send it here by putting or stuffing the data with the escape character. So depending on the length of the frame, if you have escape character here, then you know that this is not the end of the frame. So what if I have a bit pattern that looks like escape and flag in the data? The same thing applies. So you put escape before it. So the receiver will know that once I have escape character, then I have to remove it. And the rest is going to be part of the data. Okay? So once I have an escape character, then I have to remove it, and I consider the remaining part as part of the data. Until I see a flag with no escape character before it.
So who controls the escape?
I have to do it. This is one step that the data link control sublayer will have to perform. So the data link control sublayer will have to perform this byte stuffing. Byte stuffing is a technique, okay, under the category of framing. Okay, so framing will perform the delimiter, so we'll add the delimiters. But then the byte stuffing will come and say, okay, I have to first scan the data and make sure that there is no delimiter pattern inside the data. If there is, then I perform the byte stuffing. So the byte stuffing is very simple. Any flag or escape character inside the data, okay, I will have to put another escape character before it. Okay, so any flag or escape character. So we have here we have a flag, so we have to put escape character. This is part of the stuffing. This is not, escape is not actually part of the data. Okay, here we have escape character as part of the data. Then I have to also preset that with escape character, another escape character. Okay. So this means to the receiver that whenever you find an escape character, this means that you remove it. This is what actually happens here. So on the receiver side, this is the frame that I received. So when it goes to the data link control sublayer at the receiver side, okay, what will happen is that the receiver will go through the data, will find escape character. Automatically, it will remove it. And then consider the one after that as part of the data, and then go on. Here, it will find another escape character, it will remove it, and consider the one after that as part of the data, until it finds flag with no escape character before it. That's when it actually finds out that this is the end of that frame. As simple as that. Okay, so that's very easy. There's one slight problem in here. This is actually good if your data is in the form of a text. Okay, so you're sending text. That doesn't mean that if you're sending like video or audio, it doesn't work. It still works. It still works, but the problem is that I have to insert a full character. A full character meaning what? 8 bits. Okay. So if I have many flags of this in the data itself, this means that I'm actually adding a lot of overhead on the data itself. Okay. So every time I have a flag, I have to put 8 bits. Every time I find a flag or escape character. Depending on the probability of having the flag or the escape character pattern in the data, you may end up actually adding a significant part of the data as an overhead just to do byte stuffing. So what is the alternative? The alternative is what we call bit stuffing. So for byte stuffing, this is the process of adding one extra byte. So I add one extra byte, 8 bits, every time I have a escape character or a flag. Instead, what we could do is to think about the bit-oriented protocol. In the bit-oriented protocol, at the end, I'm going to transfer this as stream of bits. And stream of bits is the generic form of sending any type of data, right? Whether it's text, video, audio, anything. Anything will have to be transformed into bits. So the other idea is to try to think of a bit-oriented stuffing mechanism. So instead of putting a character, hopefully I can just insert one bit if possible. And the idea again is very simple. What I need to do is that I need to avoid having 0 and then 6 ones and then 0, right? That's what I'm trying to avoid. I'm trying to avoid this this pattern, 0 and then 6 ones and then 0. So instead of using the byte stuffing and insert 8 bits, I'm going to create some discrepancy in this pattern. So I'm going to go through the bits of the data. The bits, not the bytes. The bits. And then count the number of consecutive ones. Whenever I have 5 ones, I'm going to automatically put a 0 after that. So what will happen? What will happen is that if I have a flag that looks like 0 and then 6 ones, what will happen is that after 1, number 5, I'm going to put a 0 here. Okay? And then continue on. So there will be 1, okay, or 1, 0, if I have the flag. So if the receiver finds 5 ones, it will know that the bit after that, the 0 after this, should be removed. That's what it does. So in that case, I will guarantee that I will never have 6 ones consecutive, right? Because if I have 6 ones consecutive, if there is any 0 after that, then I'm going to stop. صح? If I have 6 ones consecutive, and then any 0 after this, I'm going to stop and say this is the end of the frame. But the bit stuffing, what it does is that it counts the number of ones. Once it finds that I have 5 ones, then automatically it puts a 0 after that in the data. Okay? So it puts a 0, and then at the receiver side will count the number of ones. If it finds 5 ones, then it should find the 0 after that. If there is 6 ones and 0 after this, it will stop. Okay, so this is how it looks like simply. So whenever I have, so this is the bit pattern that I have, and then this method will work regardless of whatever type of data you have, of course. And of course, it's less overhead because what I'm adding is actually 1 bit as opposed to 8 bits or 1 character. So whenever I have 5, here I have, for example, 8 ones. Okay? 8 ones is not the flag, but regardless, for me, I'm trying to avoid having 6 ones and then 0 after that. So what I'm going to do is that automatically I will count the number of ones. Once I find that I have 5 ones, then I put 0 after that. And then continue on. If you have here like 12 ones, that's what I'm going to do. I'm going to count 5 ones, put 0. 5 ones, put 0. And so on. So if I do that, then I will never have the flag pattern inside the data. This will never happen. Okay? So in which case, once I have the flag, then I can stop with high level of confidence. And what the receiver will do is that once it finds 5 ones and then 0 after that, it will remove the 0 and continue. 5 ones and then 0 after that, it will remove the 0 and continue, and so on. Until it finds 6 ones and then 0, then it stops. So regardless of the number of consecutive ones, after each 5 ones, I'm gonna embed some 1 0 after that. So this is what we call bit stuffing, and supposedly the overhead for this is less compared to byte stuffing, because here what I'm adding is actually 1 bit as opposed to 8 bits at a time. Okay? So any question? So the framing in general is a very easy process. Yani it's very systematic, very straightforward. Okay? So the framing part is very straightforward. This is a little bit tricky part. So the other 2 functionalities of the data link control are the flow control and error control. Flow control means that when the sender tries to send the frames, now I'm starting from here, okay, we have framing is done, so we deal with frames. Okay? So we deal with units of data. So we start sending frames now. Okay? I can send these frames if I have a video and I have, of course, what happens is that at the data link control, there is like buffer. In this buffer, I hold all the frames. The data link control, it reads 1 frame, okay, and then send it to the physical layer, to the receiver. Okay? So here I have the choice. Whenever I have a frame, I will just get the frame and send it. By sending it, I mean that I should send it to the MAC layer. The MAC layer will control the access to the medium and then send it. Okay? But then there is a slight chance that I have the receiver on the other side, and the receiver will receive frames back to back like this. The receivers will receive the frames 0, 1, 2, frame 0, frame 1, frame 2, one after the other, back to back. What might happen here is that the receiver will receive this frame and start processing it. Before it actually finishes processing 1 frame, it receives the other one. Then it stores it in the buffer. Okay, so I'm still processing. Another frame came in. It's very fast. I cannot cope with it. So what am I going to do is basically, I will start dropping the frames because I cannot cope with the speed. So flow control talks about controlling the flow. It's like the flow of the water in a pipe. Okay? Sometimes when you have like a wave, and this wave might be like very, very fast, and it pushes you away or hurts somebody, or if the flow is reasonable, then we can deal with it. If the flow of water in the pipe is too much, then we cannot use it properly. But if the flow is reasonable, then we can use it efficiently. This is the same idea. So flow control talks about the control of the flow. So what can I do here? I can just control this gap between the frames. I will send a frame and wait a little bit and send another frame. This is what we mean by flow control. But then how long should I wait? I don't know. One way is to say, okay, I will wait for 1 second, or I will wait for 10 milliseconds and send another frame. But in that case, I can waste the medium, because the medium will be idle. So one way is to always get some hint from the receiver if the receiver can cope with the flow that I'm sending. It's like when we use the faucet, مثلا, we can increase the flow or decrease the flow based on our need, right? So we can increase the flow until certain limit, and then we say, okay, that flow is good, I can deal with that. And then you start using the water. This is the same thing. I will send the flow to the receiver, and then at certain limit I have to stop. This limit should achieve two things. Should achieve the fact that the receiver can deal with it, and also the network itself or the medium can deal with it, or the medium should not be idle all the time. So I need to make sure that I utilize the medium efficiently, and at the same time I don't overflow the receiver. So that's, in a nutshell, the purpose or the main objective of the flow control. Error control, on the other side, is very clear. It's natural. It talks about the fact that whenever I have any error in the transmission, which means that the frame arrives to the receiver buffer correctly and in a reasonable flow, but unfortunately when the receiver starts decoding that frame, it finds that probably there is some error in the data. So first of all, how does it find this? Okay, so we have some bits in the header and trailer that tells the receiver whether this data is good or there is some error into it. Okay? If that's the case, then what will happen? Then the receiver should inform the sender that this frame, based on the frame ID, it sends the sender back, frame number X has some error. Okay? The other form of error control is when I send the frame, but due to some failure in the medium, the frame does not even reach the receiver. Okay? So there are two ways now. There are two forms of the error. Either I send the frame and it arrives, but the receiver recognizes that there is an error in the frame, or I send the frame and it doesn't even arrive to the receiver. ماشي? The reaction that the sender will do in that case is the same, whether the frame arrives to the receiver with an error or the frame does not arrive to the receiver. Okay? So first, the sender has to recognize that. How does the sender recognize that this error has happened? Well, if the frame arrives to the receiver, then the receiver can actually inform the sender by sending some kind of a negative acknowledgement. Right? So I tell the sender, pay attention to the fact that I received the frame, but the frame seems to be in error. So that's easy. So if the frame does not arrive to the receiver, what will happen? The sender will wait and wait and wait. And then after some time, after some kind of a timeout, it will assume that the frame did not arrive to the receiver. So the recognition of the error can happen in two forms, based on the form of the error. If there is the frame arrives but in error, or the frame does not arrive. So the sender will recognize that one of these two forms has happened, either by receiving negative acknowledgement or by not receiving anything for a duration of time, which we call a timeout. The reaction to this is very simple. Retransmit. A frame has an error, I have to retransmit the same frame. So error control talks about that. So error control talks about how to recognize that there is an error event. And once I recognize that, the reaction is very simple because I know what to do. I will take the same frame and send it again. As simple as that. So we know conceptually what flow control means and error control means. Each one of these has of mechanisms, which we will talk about in the remaining part of this chapter. So flow control refers to a set of procedures used to restrict the amount of data that the sender can send before waiting for an acknowledgement. This is a scientific definition. The idea is basically that I'm controlling the flow that I send to the receiver. Okay? So if I receive an acknowledgement fast enough, this means that the receiver is telling me I can cope with more. Okay, so in that case, I can give him more. If the acknowledgement arrives late or every long duration of time, this means that probably the receiver cannot cope with the speed, so maybe I should reduce the speed a little bit. So error control on the other side talks about automatic repeat request, which means that I should recognize whether an error has happened or not, and if an error happens, then I'm going to retransmit. As easy as that. So now let us see how the flow control and error control work. And actually, what we will see is that the data lane control deals with those two functionalities concurrently. So it controls the flow and at the same time responds to the errors. So I will control the flow to the receiver, and at the same time, when I receive an acknowledgement, this means what? This means that on one hand, I receive the data correctly. On the other hand, I can cope with the speed that you're sending. So the acknowledgement has a lot of information actually. So when I receive an acknowledgement, I know that the frame has arrived, and I know that the receiver is coping with the speed. Okay? If I receive a negative acknowledgement, this means that, okay, I don't have any problem with the speed, right? But unfortunately, this particular frame has arrived in error. So this way I can start talking about the two functionalities concurrently. So the acknowledgement will give me some information about the flow control and about the error control. The acknowledgement means there's no error. Negative acknowledgement means I don't have any problem with the speed, but the data arrived in error. So this way I can actually deal with both of them at the same time. So what we are going to do from now on is to talk about a set of techniques for flow control and error control at the same time. Okay? So for each technique, what we are going to do is that we are going to look at like pseudocode that describes how this technique works. Okay? Basically, the technique will deal with certain events. The event is that I received an acknowledgement, I have a data to send, or I received a negative acknowledgement, and so on. And it deals with these events according to a certain procedure which we will talk about. And according to this procedure, we can analyze whether this scheme is good, whether this scheme is, or this technique performs good error control or good flow control or not. Okay? So we'll stop here, inshallah. We'll talk about the rest next time.